All right, so in this video, we're going to be looking at graphs of polynomial functions. We have the expression, and we're going to describe their zeros, their multiplicity, the end behavior, and then we're going to use that in combination in order to plot the function. Now, we're going to look at two cases, one of which is already in factored form, and then one of which we will have to factor. Now, we're going to use one that we can actually factor manually as our example. But as we get more sophisticated devices like the rational zeros theorem and so on and so forth, we will be able to, or sometimes have to, use long division to identify zeros and not necessarily be able to factor them using techniques from way back in beginning algebra. But that's what we're going to look at. We're going to look at the factoring case first. All right, now this particular first example is already in factored form, so we can easily identify the zeros. The zeros are going to be x equals 0, x equals 1, and x equals -2. Because we're going to get the 0 from this one. If I set that factor equal to 0, I get x equals 0. I can set this one equal to 0, I get x equals 1, and I set this one equal to 0, then I got x equals -2. Now, the powers are what determine the multiplicity. So the 0 here has multiplicity 2, x equals 1 has multiplicity 3. Sorry, and x equals -2 has multiplicity 1. Now, this multiplicity is going to determine how we go through the zeros as we cross the x-axis. Now, in order to determine the end behavior in either infinity, we need to think about the overall highest degree term in our problem. So just count up the powers of x, basically. So here's 2 powers of x. This one's going to be 3 powers of x, so now we're up to 5. This is 1 more power of x, so that's 6 degrees of x. So this is a degree 6 polynomial. So the leading term is positive. If we multiply out, again, we don't have to do the middle details for this, but just the leading term, it's going to be positive. So positive x to the 6th. And so that means we're going to have essentially a graph that looks like it opens upward, like a U. It'll be, because it's a 6-degree term, if it was by itself, it would be really flat in the middle, but basically it's a quadratic shape, steeper, going to infinity a lot faster, but basically it's U-shaped in some fashion. So on the left, it starts at positive infinity. So when x is very small, when x is going to negative infinity, you raise a really negative number to a 6th power, it becomes a really large positive number because all the negatives cancel in pairs. And on the right, it ends at positive infinity. So if we were to then try to graph this, not a very straight line, but that's fine. We'll go to Desmos and we'll double check our graph to make sure it's qualitatively the same. We had a 0 here. We had a 0 at 1, and we had a 0 over here at -2. We're starting up here, and we're ending down here. Our zeros, the -2 was multiplicity 1, so it goes through the graph at -2. I missed it a little bit, but it goes through it at a multiplicity 1, 0. It then, at multiplicity 2, 0, is actually going to bounce off because it doesn't go through the graph, it touches the graph at that point. And then at the multiplicity 3, 0, it is going to go back through, but it's going to go through with a little bit of a kink and then end up, again, it'll be much steeper than this, but it'll end up going back to positive infinity. So this is kind of what we would expect. Again, odd multiplicities will go through the graph. Higher odd multiplicities, again, think about a cubic, it kind of flattens out and then goes through. So let's double check and see what whether Desmos agrees with this basic idea or not. Again, if we wanted more details, we could plot some additional points in the middle here to be more precise. But at this stage, we just sort of want a general idea, general sketch about what the shape of our graph is going to look like. And from Desmos, we get the following graph. Now, one thing that's worth noting here is that our basic shape is the same. We go through -2 right here. That's this point right here. And there's this big steep drop. Now, remember, we're coming down from x to the 6. So these values are getting very large very quickly. So the scale here, again, don't worry about it too much. But we drop down below, we come back up and we touch at 0. And notice we stay back on that negative side. These are very small decimal values that are being raised to relatively large powers. So this bump is very, very small. And you can see that it doesn't go straight through 1 like it did here at -2, where we had multiplicity 1. Instead, it kind of flattens out. And then once it gets through, then it jumps back up to nearly vertical because, again, x to the 6 gets large really quickly. So this is, again, it's consistent with our general idea. When we plot these functions, we want their qualitative behavior. If we want more detail, we can always plot additional points in order to get a better sense. And when we get into calculus, of course, then we'll have other tools where we can also identify these sort of mins and maxes that are in the middle between our intercepts. But for right now, this is more than enough. All right, so we have another example that we also want to look at, which I said we can actually apply factoring to. When our functions are multiplied out, if we can factor them, we should try to do that because the alternative to not being able to factor them, which certainly can happen with cubics and above, is basically that we have to trial and error until we find out what a factor is. Or sometimes we can use graphing technology, but if we don't have the technology around, then we have to just trial and error. But this one can be factored, and so we can get it into factored form without too much difficulty. Here I have to use factoring by grouping. I have 4 terms. So factor out what's in common from the first 2 terms is an x squared. And then I factor out what's in common, and I have a typo, I think. Factor out what's in common from the second 2 terms. And then I can refactor and now finally x minus 2, x plus 2, and x minus 7. Now, with the negative sign that I originally started with, that would not factor properly, and so then I would have had to start guessing possible zeros, plus or minus 1, plus or minus 2, plus or minus 4, plus or minus 7, plus or minus 14, plus or minus 28 would all be viable possibilities that I would have to test to see which one worked. But here, because I fixed the sign, we were able to actually do the factoring. And so now we have zeros at 2, -2, and 7, and all are multiplicity 1, which means we won't have any bouncing going on. we're simply going to pass or kinking, no flattening out before it passes through. It's just going to go straight through the x-axis at each one of these points. And this is a cubic with a positive leading coefficient. So the graph starts at the bottom left, because when you put in a very large negative number into a cube, it gets even more negative. So it stays negative because it's an odd power. So bottom left and ends at the top right, because again, positive number cubed stays positive, just gets bigger. And so those become the dominant things outside of our sort of zero region. Now, again, we're going to try to graph these, again, just to get a sketch of what the general behavior is, and then we'll look at the technology. So we have zeros at 2, -2, and 7. We've got a 0 out here, we've got a 0 out here, and we've got a 0 out here. We know the y-intercept from the original problem is going to be 28. So it's going to pop way up here. So up here someplace. But what we also know is that it's going to start very negative. It's going to come back up. It's going to go way up there because of the 28. It's going to go straight through at 2. And it's probably going to go way down and then way back up. And then finally end at positive infinity. And so let's check Desmos and confirm that this is the general behavior. And when we plot this, we can see that we do indeed get our zeros. They go straight through and they go off to infinity in the way that we described. And so this does look consistent with, again, the general behavior of our by hand plot.